yesterday's lecture. So, there. It's all working. I can see what the next slide is over here. So we're talking about resonance, and we're going to blow through the rest of this chapter pretty quickly, and then we're going to go on into chapter 4. This chapter is basically done almost. And we're talking about the 4 things, right, for resonance. And so I just wanted to remind you, we look at the atom. What's important about atom? Electronegativity and size, right? So you look at the atom that is, generally we look at the atom that's connected to the acidic hydrogen. It turns out, we'll see today, it doesn't have to be one directly connected. It could be the one through resonance that's connected. Okay. But then resonance is important. What's important about resonance? More resonance is more stability. More resonance contributors that you have, the more stable the ion can be, because that has, what does it allow the charge to do? Spread out. Yeah. Third one's induction. What's induction?
Pulling the negative charge away from the acidic side of the atom.
Yeah, basically it pulls electron density, creates a positive dipole, and that positive dipole helps to pull electron density away from the negative side of the atom. So that's good. What do you mean by orbital? Hybridized orbital, right? SPs are more stable with the negative charge than sp3s because the sp orbital is what? Smaller. Yeah, so it holds the electrons closer to the nucleus. So good. I think you guys are all there with me. So REO is generally good. Did I talk about this slide? Generally good, except for in this particular instance, it's not. So if I were to compare acids for strength, like, which acid is stronger? You might say, well, nitrogen, because REO, atom's the first thing, right? Nitrogen's more electronegative than carbon, so you might automatically assume that this nitrogen, the hydrogen on it's going to be more acidic than the carbon. And this is one of those exceptions that you just have to remember. Okay? So it's actually the other way around. See, I guess to determine the actual acidities, right, you have to know that. But if you had always had the pKa values, you would never have to learn this stuff, okay? So I'm just saying that's a nice statement and everything. And the truth is, like I said, if your life depends on it, and somebody says, your pKa values are your life, well, it could happen. I don't know. And I lived in this little weird chemistry world with 6 children and a wife who's a chemist. So, what's that?
Silicon Valley or something?
Silicon Valley, no, not even there. I don't care about these things. So now, well, they might. I shouldn't say that. So yeah, if it really matters, you will look it up. But a lot of times you don't have time to look things up. You're just trying to get a general sense of how things are going to go. Okay. So in fact, what ends up happening is the pKa of ammonia is much higher than the pKa of acetylene. Hi, I'm recording you guys as you come in. Say hi.
Hi.
Good. I won't say your name. Joke, but okay. Now, so weaker acid, stronger conjugate base. This equilibrium is really favored towards this side. Remember, it always goes to the side of the higher pKa. And we often use amide to pull hydrogens off of those carbons, and then we generate that acetylide ion. That's what we call it, acetylide. This guy. Oops, see, we've got to get a pen, and then go acetylide. As a nucleophile, because it has that negative charge, and I think I did mention that yesterday. So, all right. So, did we do this slide? Hey, this is where it gets good. You guys in this class in particular are always at a good breaking point when I stop lecturing, because then I can just kind of roll in. The other class, I hope you're not listening to this lecture. It always at some weird place. I'm like, okay, I got to start really far back, or I got to skip some stuff, and I can just not be there. 7:30 in the morning. Okay, now. Yeah, if I wasn't a teacher, I might not be there. So what we want to do is we want to rank acids from strongest, acidic hydrogen strongest to weakest, because you get a molecule and you put in a strong base, which hydrogen is going to come off? That's going to determine where it reacts. And is that the appropriate thing that you want to happen? So what do you think is the most acidic hydrogen? HD, right? Because you go through the list, like Oreo, atom first, right? So atoms first, oxygen's the most electronegative. That's the most acidic hydrogen.
This one is the most likely, it's the first to break off.
Yeah, so if I put a bunch of strong base in here, this would definitely be the first one to come off. Well, okay, I gotta qualify that a little bit. From what we've talked about so far, seems like the most likely one to come off. A lot of times in organic chemistry, things are kinetically determined. So whether or not something's more stable when it comes off, see, this is the lie about the whole stability thing. You thought I was always telling the truth? We have this term, kinetically more stable, which means it's actually not the most stable, but it's the one that reacts the slowest, and it's stable because of that. So I can still say stability is the answer for everything, but then there's this kinetically more stable, which is kind of a lie. All right, but you'll hear it later when I talk about it. So this one will come off the oxygen, so that's the strongest. So I'm going to rank that number 1. And you know the way my brain works is I always go from either the strongest to weakest or the weakest to strongest. That's actually what I like to do, because then I know everything else is in between. Okay? So what's the weakest? What's number 4? H. A? B? Or C? I think they're only choices because D's gone. How many people say A? How many people say B? How many people say C? How many people have an idea? Come on. Okay, atom. Is it the atom that matters here? No. What's the next factor? Resonance, right? So this one will have resonance. So this is probably the second strongest. Okay. Third strongest is induction. So it also has induction here, right? So it has 2 things going for it. Probably the second strongest. So let's do number 2 then. You guys don't like my method of trying to figure out which is the worst. That's okay. Oh yeah, sorry. Did I do that?
Yeah.
I did not. Cover up. A conspiracy theorist. Now, what are the other factors? Induction and orbital. And what is more acidic in terms? Well, do these are only 2 left, right? A little inductive effect here, but it's not that important.
So the orbital is more important.
Orbital end up being more important in this case. This is on an SP2, or SP2. So this will probably be more acidic than this because that's on an SP3. So I would say this one is 3, and this one is 4.
How's that one on SP3? That it would be SP2 as well.
What's missing here? Yeah, it's tricky. You got to make sure you do that. This inductive effect is weak because normally when we talk about inductive effects, we're talking the strongest inductive effects are right next to it. This one's 2 away. It's a little bit tricky, but I'm pretty sure it's not going to outrank the hybridization in this case. What about this one? Good, there's my pointer. Woohoo! So I got that, this hydrogen versus this hydrogen versus this hydrogen. I don't know if it records that or not. But. Strongest. A. Why A? Because we're looking, what's the first thing we look at? Atom. Okay. So this one is number 1. Now we're left with this versus this. So, is it the atom? No.
No.
Is there resonance? No. Well, no, because if you're thinking of this, remember resonance has to be a p orbital adjacent to the pi bond. So this p orbital is not this p orbital that's making this pi bond, right, is not adjacent to this atom. You have to have, if to have resonance here, you have to have a bond here and another hydrogen. Okay? The hydrogen would have to be this one that's acidic. Make sense? So if I think about resonance, this one's a little tricky. You do have resonance on this one, but you have an sp2 hybridized one over here. This resonance, right, if you get rid of that guy, it can go like that.
So it would be just like the double bond.
Right, and then yeah, it's an allylic lone pair. Right. Those hydrogens tend to be a little bit more acidic. So that's going to be more important than this. So order, what did I just say? 1, 2? I haven't actually looked these values up. 3. So what I really want you to do, but you see how I did that? I went through the list. I'll give you like 4 things on a structure. Find the most acidic, do REO for all of them, and then justify which one's the strongest. Atom generally usually wins, then it's usually resonance, then it's induction, and then it's orbital. All right. Questions? I'm going to skip a few things. Well, okay, I'll do this one. So sometimes we have acids that look like this. They carry a positive charge. And most of those acids are amine type acids or things that have been protonated, so they have a positive charge. You can also use REO to predict which one's the strongest and which is the weakest in these situations as well. Oxygen and nitrogen, which is more electronegative. Oxygen. So if you're going to sort these things out immediately, that's what the first thing that I would do. I would look at the type of atom that it's connected to, and then these two are on nitrogens, right? So I have a nitrogen here, and I have a nitrogen here. So the oxygen ones all be stronger, nitrogens will all be weaker. And then all you do is you sort the nitrogen ones. Inductive effect here, no inductive effect here, okay? So this is the weakest of the bunch. You see how I'm doing this? So I grouped it by atom. Now I'm looked at the nitrogen groupings, and then I said, okay, inductive effect here. The atom doesn't matter. Neither one has resonance. Inductive effect here, no inductive effect here. So this one is the weakest. I'm not going to go through the organization of all of these, but I will go through just the strongest and the weakest possibly. That's the weakest. Now, which one's the strongest?
Can't be the second.
Can't be this one. These hybridization it's all atom, right? Atom's all the same. There's no inductive effect on any of them. This one has resonance when this goes away. This pair can donate here. Okay? No resonance here. That's not resonance. So now what you have to decide is which one of these two is going to be the strongest acid. Yeah, so this one I'd have to throw up and say, well, I think this one has resonance and this one has sp2, right? And then the order that you're taught in REO, it's resonance first. So this is going to be this. For acid strength, this will be the strongest. So anyways, you can sort them out like that. That's the whole idea. Have you guys go through and indicate why you think. I might give you a list this long, I might not. Depends on how much explanation I'm asking for. When you see a test and it has this much space to write the answer in, right? It's probably a few words. If there's this much space, then it's probably more than a few words. Like I give you the whole page to write. Okay? I do this as we go on in OChem. I'll give you a reaction mechanism until you draw the entire mechanism and explain the steps. It takes a page. Okay? By the way, everybody loves those questions. Okay, I lied again. Okay, so now what we want to do is look at predicting equilibrium positions. But basically it goes like this. The stronger acid always wins. Okay? So if you know the pKa values, just look at the pKa values and then there's no like discussion. It's like that's just what it is. If you don't know the pKa's, then what you have to do is look at the relative stabilities of the conjugate bases and determine which acid's stronger based on that, and then the stronger acid wins. But it always comes out to be the stronger acid wins the equilibrium. And by that I mean it pushes the reaction to the other side. Okay? So the side opposite the strong acid will always be higher in concentration than the side with the weaker acid, than the side with the stronger acid. Okay, so now we don't have pKa's for this. So we got to figure out which way equilibrium is shifted on this guy. These structures, basically the same, right? Yeah? Except this guy here, right? And that guy there. I get a little arrow. I like my little arrow. I'm really happy with him. I'm so used to doing this. I won't, anyways. There's a whole side of my teaching that just suffers because it's all internal. You know, it's this struggle in my brain. But I am this kind of person that usually talks about these internal struggles, so they're not really internal. Okay, so now, atoms the same. A little more inductive effect with the oxygen, right? They both have resonance, and they both, have the same hybridization. So how would you predict which one's stronger? It turns in this case, you have to look at the conjugates and determine which one of these is more stable. Okay? And because they have resonance, you have to look at the resonance structures. So I am going to draw their resonance structures underneath, hopefully, and not some horrible handwriting, but let's see if I can do this. Oops. Like that. Oops. Look at that. That one's wrong, right? Have that. And on the other one I have similar structure. So those are the resonance structures. And to do that, all I did was I took these electrons and I pushed them like this. This is an allylic lone pair. I love how he classifies these things. That was another one of those internal commentaries that I just have to say. So, which of these two is more stable? The sulfur, because it's bigger, right? So it's back to the atom again, right? So now, even though they have resonance, this has an inductive effect. Back to the atom, the sulfur's bigger, so it can distribute the charge better, right? So which of these is more stable? Sulfur one. So that means this is the stronger acid. So the equilibrium should be shifted to the left. Okay. I don't have the pKa's. I didn't look them up. They're probably in your book somewhere. But actually, is it on the next slide? Maybe. I don't know. No. Okay. So the other thing that you can do is if you want to determine the position of equilibrium, a lot of times a lot of times we determine the position of equilibrium. A lot of times what we're trying to do is say, okay, I want to generate a certain anion. So I want to pull a hydrogen off of this, or I want to pull a hydrogen off of this, or I want to pull a hydrogen off of this. And so you have to figure out what base you use for that. Simplest thing to do is just look up the pKa's for all the acids. So for example, for an acetylide ion, the pKa for the acid for that, I did it again. So, flipping back in the book and looking at the table, it's 25. That's for C triple bond CH. If I remember, this one's about 21, 22. That is for, you look for something like this. Oh, actually, I think it's 18, sorry, or 19. But again, you just go to the table and you look it up. This one, this one is 4.75. And the only reason I know that one so well is because it's the one we use in Chem 1B all the time. That's acetic acid. But that's actually for this acid. So I'm looking up the acids of these guys. So how am I going to remove the proton from this to make that? Well, I just have to find a base, right? That is, or an acid whose conjugate base that I can mix it with that is stronger than this. So for example, let me do this on the board. Okay. That's a weird marker. So I want to do this. And I've got to add a base to it. And the base will have a pair of electrons and pull off that hydrogen. And I'll end up with this. All right, so this is the acid. pKa for this is 4.75. So this acid, the only thing that has to be true is the pKa has to be greater than 4.75. It's like NaOH would work. It's around 15.7 or something like that. Right? It's pretty high.
Does that matter?
Is that?
Does it matter how much higher it is?
Oh, well, actually, so I'm sorry. I said NaOH, but the acid that we're looking at is H2O. So, because that's what HB, if this is OH minus, this is going to form H2O. So yeah, does it matter like how much stronger it is? Well, if this is 4.75, and because I like simple numbers, and this was 6.75, right? That's 2 orders of magnitude. You'd have a 100-fold favoring of the product over the reactants. That whole magnitude of the difference in the equilibrium constants. So if I use sodium hydroxide and I get 15.75, right? That's 15.7, but let's say 7.5. Then it would be 11, right? So it's 11 orders of magnitude favoring to the product. We'd have essentially a complete conversion of this to its conjugate base. If we did acetylide, water formed an acetylide ion, all we need to do is find an acid that's weaker than this, whose pKa value is higher. Right? And the one that's typically used for that, because it's convenient, is this one. This is the acid, pKa is about 35 or 38. Your book says 38. I've always said 35. So. It's like when you're that many orders of magnitude away, it doesn't really matter. But it is important. I shouldn't talk about it so trivially. For 18, if it was 18, what do? Yeah, anything higher than 18. So that's all you do. You go to the table of pKa values and you look it up. If you don't have the pKa values, then you have to do REO. Right? This whole thing that we've been doing the last day or so. So any questions on that? It's much easier with a table. And you'll get questions like that. I'll give you a table with some values, not all values. Because when I gave you all values, when you did REO, you would just look at the values on the table and say, well, of course this one's stronger, and then you would list your REO and always be right.
Don't we know all the pKa values for everything?
Not always. Yeah, and these pKa values are generally measured in water, right? The ones between about 0 and 15 or so. And then if it's not in water, the pK values are all different. Okay, so you have to judge based on, yeah, we can use the water values to extrapolate, but they don't always extrapolate the way you would like them to. And we'll talk about that today, actually. I'm going to skip. You can do that. Okay, so solvent. Solvent's an important thing. Why is solvent an important thing? Okay, so let's do this. Who wants to be an ion? Anybody want to be an ion? Oh, you came in late, huh? You're an ion. Stand up. Both of you, both late. Okay. You're both ions. Okay, who wants to be positive? Okay, are you sure?
Yes. I'm positive.
There we go. It's an old joke, right? Okay, so these guys are relatively small ions, right? And so you're a negative ion, right? So go over there. How are you going to be more stable? Yeah, right? Now, I'm a water molecule, right? So part of me is positive, part of me is negative. So since you're a positive, I would have to put my negatives, and I always make this my negative side, but some people say that's my positive side. That's so I would be like this. I'd be grabbing him, dragging him off, come here, like this. And then I separate them because I'm a water molecule and I make them more stable. And while I'm pushing him this way, I'm pushing her that way. And a bunch of my buddies, like Oscar, this whole row, just grab her, run away with her. The rest would grab her, run away with her, okay? But let's say that I had a big, bulky backside, okay? And that my charge was like buried inside the big, bulky backside. And I wanted to separate these two. So I have a positive charge on the surface over here, okay? But the negative, well, okay, so I'm making this my positive side, remember. My positive side is on the surface right here, but my negative side is buried, like in a pile of junk, okay? It's a joke there. So I'm the positive side. I'm really good at like taking care of her, but him, because all the negative is buried, I can't quite push him out of the way because I can't stabilize him. It's all about stability. So if part of the dipole is buried, then the moral of the story is it can't solvate or stabilize the ion as well. Because the ion can't, like, that's maybe my backside was that big. That's as close as I could get to him. Right? And the closer two ions, two charges get to each other, what do we know? Opposite charges, as they get closer, they become more stable. So I can stabilize her, but I wouldn't be able to stabilize him. Make sense? Now that you're standing up here by my big, bulky backside. Okay, have a seat. Okay, who else was late? No, never mind. That wasn't as embarrassing as you maybe thought it might have been. Okay, so let's look at a couple of examples of this. And, this slide's actually mostly about the leveling effect, which I talked about earlier, so I'm going to skip that leveling effect stuff.
Can you repeat what you said again? You said if you have it's covered your charge or something like that?
Yeah, so if I bury, and I'm going to show you how you bury a charge in a compound. If you bury a charge in a compound so that it's not accessible, then it's not able to stabilize ions as well, okay? So look at T-butanol, right, and ethanol, and you'll look and now I'm sort of reversing the argument because I'm looking at the acid. pKa is 18, pKa is 16. And based on REO, they should be the same, right? But this is pKa's in water. If it's not in water, it's a different argument. Actually, you can change things. But they're different by 2 orders of magnitude. So ethanol is 100 times stronger acid than T-butanol. Okay? So if you were to analyze these molecules and place dipoles on them, where would your dipoles be? Where, let's just do this because they didn't do that. I'm going to draw H here. So ignore their H. I'm going to draw an H here. So I can draw all my dipoles in. Where's the negative on the T-butanol? This is called T-butanol. Tert is abbreviated as T. I can't say tert. It just sounds weird.
Oxygen.
Huh? Oxygen's the negative, right? And where's my positives? Hydrogen and the carbon. And this one is negative, and this one is positive, and this one is positive. Okay, now, remember this is an equilibrium reaction.